Well, hello everybody, Dave here, and this is the second lesson in a series of lessons on the idea of exploring data. In the last lesson, we actually talked about how to deal with categorical data. Now we're going to do our first lesson in trying to understand what to do with quantitative data. And in this lesson, we're going to specifically focus on how to actually create visuals to display the data, where the last lesson will be dealing with how to now take quantitative data and start to perform some calculations of some use in statistics. So the first plot we're going to talk about is one that we actually saw in the last lesson, and it's called a dot plot. And a dot plot is a nice, easy way to take a data set and give it a visual without much work to be done. You simply have to create a horizontal axis with an appropriate scale, from minimum to maximum according to the data set, label it appropriately, which in our case is the number of goals scored by the US women's team, and then for each data point in the table, you are going to make a single dot. If there's more than one for that value, as you can see from the picture, you simply stack the dots on top of each other. This is powerful because now we can see two things. We can begin to see something about the overall distribution of this graph, and we can also see that there's a couple of points out there on the far right at 13 and 14 that maybe need some addressing. So now that we have the plot, we're going to want to start trying to analyze it. And the way we do that to begin with is examine it based upon the properties of SOX. And SOX is an acronym that stands for the shape, the outliers, the center, and the spread. And so when we're referring to the shape, we're going to talk about, is it symmetric? Is there some sort of funny pattern that we have to talk about? Are there points that are a far distance away from the overall shape that are worth talking about? We would refer to those as outliers. Is the center a certain value? Can we determine what the center is? Is the spread something to talk about? Is it fairly spread out? Are they tightly packed together? All of these ideas are physical properties of the graph that we're going to want to analyze so that we can compare them to other graphs dealing with similar variables. So when describing the shape, there's essentially only three ways that we're going to do so. We're going to refer to it either as symmetric, skewed to the right, or skewed to the left. Now, symmetric is pretty easy to tell because it looks generally balanced. One of the things that's key in statistics is to recognize that we're not going to split hairs. And what I mean by that is, yes, I see that there's a little dip there at the number 8, and I see that 4 and 5 look pretty low, and then it jumps up to 6. But again, take your hand and kind of run it up and around that particular distribution. And what you see is essentially something that's symmetric. What a lot of people do mistakenly early on in statistics is they always try to indicate that there is a minor skew. It's worth getting used to the idea that we're not talking about perfect functions, we're just talking about raw data tables. So that would be definitely symmetric. Now when it comes to skew, it is commonly misused in regular everyday language because skew has generally meant something different than what it means in statistics. In statistics, when we're talking about something skewed left, you can see that we have a nice long tail pointing towards the left, and the clump of the data is actually to the right. If you look at the skewed right, you can see the clump of the data is to the left, and then you have a nice stretched out tail to the right. So this idea of a tail is the essence of how you're going to determine the skew. And just imagine grabbing the left or the right side of a symmetric distribution and pulling it out or stretching it out. Whichever direction you're stretching it out would be the direction of the skew. So please make sure that you don't use what you might have used to use when it came to the concept of skew, and understanding that really the long tail is pointing in the direction of what the skew is for that distribution. So if we took a look at an example like this, and we're talking about household sizes in two countries, and we have households in South Africa and households in the UK, and you were asked to describe this in terms of SOX. Well, if we take a look at the shape first, what I see in South Africa is something that is generally skewed to the right. I know that because I have some outliers present there, probably at about 26. That 15 one might be an outlier, so I wouldn't be concrete about it, but I'd say certainly the potential existence. But outside of that, for the most part, that data is skewed to the right. If we talk about it in terms of the center, I would say that the center is somewhere probably around 7. And the way that I did that is essentially take a look at those outliers, try to find kind of the middle of the clump that's left, and it's somewhere about 7. You will definitely have a mathematical tool after next lesson that will help you make that a little more concrete. If we talk about now the spread, we can see that we have values around 3 all the way up to about 26. But if you even look at the major clump itself, you can see that it's not as tight as the one dealing with the UK. If we look at the UK one, we can see that there's really only a difference of about 5 for the values from minimum to maximum. They're all generally clumped together. This thing looks generally symmetric, and I would say that the center is somewhere around 4. There's no outliers present at all. Now, when they want you to compare the distributions, the key thing here is to not simply list socks. It is to compare socks from one distribution to the other. So when I want to go and make the overall comparison of these distributions, I would say that the distribution of South Africa is skewed to the right, whereas the one for the UK is generally symmetric. The center for the South African distribution is somewhere around 7, whereas the center for the UK is around 4. I would talk about that in terms of it being greater instead of just saying one is this where the other is this. So I would say the center for South Africa is actually greater than the center for the UK. I would say that the spread for South Africa is larger than the spread for the UK, and I would try my best to use whatever values I can at this point. So I would say that the main clump ranges from 3 to 12, whereas the UK ranges from about 2 to 6. And so you start trying to put numbers to it. You're doing a comparison by using Boolean expressions, saying that it's greater than, less than, equal to. In the case of shape, the best you can do is talk about it whether they are both symmetric or if one's different, what the case may be. So more is better when it comes to these comparisons, so long as you use socks, so long as you talk about the direct comparison of the ideas of socks themselves. Another plot that we could deal with now is something called a stem plot. And a stem plot is going to behave very similar to a dot plot in that we're going to be able to look at it and get a sense of distribution, get a sense of center, and things like that. But what's different is a stem plot now is going to take the actual data values themselves and create the graph from it. So unlike an actual dot, you will physically see the data values in the stem plot itself. And the basic way that this works is we take any value in a data table and we turn it into a stem and a leaf. And this is typically the first or first 2 or first 3 digits. And then the leaf is that final digit, because what we're going to do is we're going to organize them very much in a similar way that we did with a dot plot. But in this case, we're going to be able to deal with different types of data. They're not going to just have to be integers. When we have all of the stems, we are going to list them vertically from smallest to largest. We have to make sure that even if the stem doesn't exist, we're going to go ahead and list it anyway. So if we have stems that are 2, 3, 6, 7, we would still show the numbers 2, 3, 4, 5, 6, 7. From there, we would write each leaf and then arrange the leaves in numerical order and provide a key for what it means. Without an actual reference to the graph itself, this could be kind of challenging to understand. So let's go ahead and take a look at what one looks like. Here's a data set of 20 female AP students and a response to the question, how many pairs of shoes do they have? You see that we have 20 values and they're 2-digit values. The first step in creating a stem plot is first identifying the stems. And to do that, we are going to take all the 2-digit values and we're essentially going to chop them in 2. We're going to have 5 and 0. We're going to have 2 and 6. We're going to have 2 and 6. We're going to have 3 and 1. So that front value, the tens digit in this case, is our stem. And the ones digit in this case is going to be our leaves. So even if we don't have all of 1, 2, 3, 4, 5, you still have to represent them all in the stems. The next step now is to add the leaves. Now I did this without arranging it numerically first. I just went through the data table and I found that when my stem is a 1, the first value is a 9, and then the next one's a 3, and a 3, and a 3. And you absolutely represent the repeats because, again, we're trying to create a graph that represents the distribution and it represents the data itself. Once we have all the leaves, we're actually going to put them in order, and then we're going to add a key that shows us what it represents. So to read this graph, it could mean a lot of different things. This could mean 49. This could mean 4.9. This could mean other things as well. The idea is within the stem plot, we have only integers, but when we create a key to represent what the stem plot means, that could actually represent various types of numbers besides integers alone. But you can see with a stem plot, we still get a chance to actually look at it and determine the shape. to take a look at the spread, to talk about if there's outliers and things like that, because we can physically see the data essentially stacked according to the leaves. So a stem plot is very nice in that it still gives you the data table directly, but it also tells you very quickly the various aspects of socks that are going to be important to us. Let's say now that we actually want to compare two different data sets, and we have a set with females in the number of shoes and males in the number of shoes. And we could make two separate stem plots and that'd be fine, but when we're talking about comparison, we really like to have things stacked, we like to have things back to back, we like to have things close together so that the comparison's easy. Perhaps you remember dealing with the segmented bar graph in the previous lesson. And so in this case, we could make what's known as a back-to-back stem plot using split stems. And what I mean by split stems is instead of just counting up from 0 to 5, we would actually split it into 2 zeros, 2 ones, 2 twos, 2 threes, 2 fours, 2 fives. And now for the first stem 0, you would put all the numbers from 0 to 4. And then for the second stem, you would put all the leaves from 5 to 9. And you do that for 1, so you can see for the males that that first stem for 1 has all numbers from 0 to 4. And then if there were any numbers from 5 to 9, you would list it there. And one of the benefits of having a split stem is that when you graph them, you can actually see a little more structure than you might have seen from just a basic stem plot alone. When we take a look at the female distribution here, you can now see that there's a bit of a gap between 3 and 4 because we couldn't see in the original stem plot that there are no values from 0 to 4 in the leaves for the females. So that's very interesting because that can help us to describe perhaps if there's any things that depart from the overall distribution. The power of the back-to-back nature of this stem plot now is the fact that we can make direct comparisons. We can see that the center of the females is generally higher than the center for males. We can see that the females is far more spread out than males. We can see that males have potential outliers. And we also see with the females there's a potential little structure there around the end of the 4 stems and the 5 stems, which may be interesting if we had some calculations to deal with as well. So now that we do the back-to-back, when we talk about socks, you are being forced into the direct comparison idea, which means those Boolean expressions as a way of describing them becomes far more obvious to you with this. So it is a powerful tool. I wouldn't default to the split stems, but I would certainly always consider whether splitting may give you some more information than having a basic stem plot alone. So the last type of graph we're going to look at is called a histogram. And you may have seen a histogram in other aspects of your education, but you may have mistakenly called it a bar graph. And they look a lot like a bar graph, except for the fact that there's no space in between the bars. And this will become an important element of the histogram when we talk about it more. Now imagine having a data set of 100 different points, and just graphing them individually just seems like a laborious task. That seems insurmountable. But instead of doing that, maybe the ultimate goal is to find out the actual count of a particular range of values, which may give us some more information. For example, when we're talking about grades, you typically don't necessarily need to know every single individual percentage. You could talk about it in terms of 5%, 10%, 20%, whatever you need. So in this case, you can actually take a data set and organize it according to these bins, or in general, they're called classes. And so to build a histogram, the first thing you do is this exact thing. Take your data set and split it up. From there, you simply count how many fall into that bin. So imagine doing laundry and having to sort according to whites and colors and other things like that. And then you simply go and you throw your data into these bins, and then you simply count how many of each are in those bins. The final thing you'll do is actually label your axes appropriately and draw the histogram itself. And again, when you label the axis, you're going to label it in such a way that it looks like you're just simply counting up by whatever your width of bin is, 5, 10, whatever the case may be. But what you'll realize is when we read the histogram, we're not going to necessarily just read it as 0 to 5 and 5 to 10 and 10 to 20. So let's take a look at an example of this. And here's a big set of data which is talking about the percentage of residents born outside of a particular state. And looking at this alone, making a dot plot may get us somewhere, but a dot plot alone would be really difficult because we're dealing with decimal numbers and there's a whole lot of them, 50. And so instead, I would rather organize them according to percentage, and perhaps this would tell me something different. So the first thing I would do then is divide it according to these bins. And so I'm going to do the bins of 0 to almost 5, 5 to almost 10, 10 to almost 15, and so on. And this almost part is absolutely essential, because the way that I've written it out here for you is to represent the continuous number line. And within this continuous number line, I've never double counted the number twice. So you'll notice in the first bin, it goes 0 to almost 5. Well, if I get the number of exactly 5, now I know not to put it in that bin, but I put it in the second bin, and so on and so forth. And so when you do this, you can then create a table, which according to your classes or your bins, you have your final counts, or if you so desire, you could create a relative frequency table and calculate it based upon the percentage of the total. From here now, we can begin to actually build the histogram. So the first thing you did, as we say, is label the axes appropriately. And in this case, because we're dealing with count and not relative frequency, the vertical axis is dealing with the number of states. The horizontal now is the percent of foreign-born residents. And in this case, notice that we count up 0 to 5 to 10 to 15 to 20 and 25. Well, when we graph these bars now, you'll notice that we're still graphing bars with no space in between because we're representing this continuous number line. And so that first bin, that first bar, is all of the numbers from 0 to almost 5. And then that second bar is going to be 5 to almost 10. So to understand the scale and how you read the bars is you simply look at the left number on the bar. And the left number is that number that is absolutely included in the bar. The second number on the right side of the bar is now the almost. So if we look at the third bar in the middle of the histogram, you can see 10 and 15. Well, to read that, you start from the left and say 10 to almost 15. So this histogram now gives us an understanding a little bit about what's going on with the data itself. Now, this bin width thing, especially when you're using a calculator, is going to be essential because a calculator is going to default to some weird-looking bin number. So you're going to need to go through understanding how to create histograms using your calculator to really understand how to set the bin width appropriately so that we can see, hopefully, some structure that allows us to make meaningful conclusions. What you definitely don't want to do, though, is pick bin widths that either hide structure or add too much structure. And what I mean by that is I wouldn't want to pick a bin width of, say, 15. Because then we would have a really large bar and a really small bar, and that wouldn't really tell us anything more than we would want out of the data itself. If we picked a bar of, say, 2, well, that's not going to be very useful either, because what we'll see is a whole lot of little narrow bars that don't necessarily tell us much of anything. So picking a bin width is essential to really gleaning the information out of a data set that we're going to need. There's a couple of important things to worry about when we're dealing with histograms. The first one is to recognize histograms from bar graphs. There's no distances between the bars, and the horizontal scales represent quantitative data instead of categories. That's your big tell when you have a histogram over a bar graph. The second thing is with the histogram, you have these counts, but those counts don't represent the individual data points. It represents the count for that particular bin. So you don't want to use the counts or percentages as data themselves. You will have to have a different data table that actually has the individual data points from which you were able to create the bins that created the histogram. So please don't use those histogram counts as data themselves. The third one is always try to use percentages instead of counts on the vertical axis when you're trying to compare distributions, because counts may not make sense if there are different counts for different studies. But the relative percentages, much like when we dealt with categorical data and the idea of a pie chart, relative percentages can at least give us an understanding of relatively looking at the sizes, if they're similar, if they're different, and things like that. But the counts alone, you may have one particular data set that has 1,000 of something and another data set that has 300 of something, where if you compared those counts, it's obvious which one is larger. But that may not be meaningful information. And number 4 is just because a graph is going to look nice, it doesn't necessarily mean that it's meaningful. One of the key things about a histogram is selecting the right bin size. In the example that I gave you, it told you that it was 0 to almost 5, and that means that you're basically counting up by 5s. If you count it up by 10s, you're going to lose some structure. If you count it up by 2s, you might see some pretty fancy structure, but in itself, it might not be meaningful at all. So please make sure that when you make a histogram, you choose a bin width that gives the best impression of what the distribution looks like without either hiding the true distribution or accentuating it too much with silly little bars of bin width 2. So folks, that's it for this lesson. I encourage you strongly to go practice how to make all of these because they're going to be graphs that you're going to use repeatedly in this chapter, the next chapter, the next chapter, and all throughout your education in statistics. So good luck to you, and we'll see you again.